degree at the University of Amsterdam. He's been at Chicago, Cambridge as postdocs, and he's been a professor at Utrecht for many years. He is a speaker at the Third European Congress of Mathematicians, member of the Royal Netherlands Academy of Arts and Sciences, and member of the Academy Europea. He's won the Descartes-Huygens Prize and the Spinoza Prize. And I believe he's written 6 books, is that right?
I didn't count.
Okay, so I organized this together with David Blank, and we got our funding from the International School and the Faculty of Sciences. And our chairman is Yuval Ginosar. Maybe you can join me in welcoming our speaker.
Thank you very much for this kind introduction. Am I on?
Is the microphone on?
Let's just, can you say one more thing?
1, 2, 3, 4, 5.
I believe so.
You have to start from 6.
6.
Is it on?
5.
Yeah, okay.
Maybe it should do.
The chair here.
Well, I'm quite honored to be given the opportunity to speak in this prestigious series of lectures. So I thank David and Oren for organizing it. And it's a series of 3 lectures. And the first one will be quite general, so with very, I will expect very few preliminary knowledge from you. I'm aware that there are some people in the room who know more about the subject than others, and perhaps know more about the subject than I do. So I will wake them up when I will try to say a few new things at the end. The second and third lecture will be a little bit more advanced. I will require a bit more knowledge of algebraic topology. But I hope I will still try to succeed in still trying to make them accessible. So, so the 3 lectures will be about operads, and operads are meant to control operations, algebraic operations that exist in topology. Now you all know that topology is about the deformation of space, and you can have a space with a nice algebraic structure. For example, a torus. You can multiply points on the torus. But what happens if you start deforming such a space, as we do in topology? What happens to the algebraic structure? And in the torus, you have nice properties like the associative rule. But if you start deforming the space, you lose the associativity. What happens to the associativity? Yeah? And what will happen is that in the deformed multiplication, there will be a path from a multiplication like this to a multiplication like this. Right? And in fact, there will be an infinity of multiplications on this, an infinity of operations on this deformed structure. So the theory of operads is meant to control this. And this infinity of this infinite system of operations has itself a topology. So you can study what topological means, the space of operations. Yeah? So I will give you some very first example of this, which goes back to the 1960s, in fact, and originates with Jim Stashev. So he says the following: if you so on the deformed space, there will be a path. Let's call it P, X, Y, Z. There will be a path from one multiplication to the other, multiplication of 3 elements. And so, in fact, you can think of this as an interval of new operations with 3 elements. For each point on the path, you have a way of putting these 3 points X, Y, and Z together. But then what happens to the higher operations if you insert more variables? So I will draw a picture. So if you have 4 points, what happens to this associative rule? Well, you can take this path and multiply it by W. You end up in this point. Okay? Or you can view the multiplication xy as a single point and take this path. So that's, strictly speaking, is a path for a different parameter, for xy, z, w. You end up in xy, z, w. Okay? And you can continue like this. Here you can view zw as a unit, so you end up in x, y, zw. And now I have moved all the parentheses from the left to the right. But I could have done that in a slightly different way. Here I can view yz as a single point. So I get into x, yz, w, x, yz, w. And then I can do it inside here. And I end up in the same place. So let me put one more name of the path. So this would be the path for x, y, z, and w. Okay?
X. That's the other.
Sorry?
No,
X times, I'm sorry. X, thank you. X times p, y, z. The diagram is already too big if you're too close to the board. Okay, so there will be a space of operations. If you deform, there will be a two-dimensional space of operations. This space is called the Stashev polytope K4. 4 because it concerns the multiplication of 4 points, K4. And there will be an operation on the deformed space like this. Okay, this is K3. So there will be K3 is just a line. Okay. So here you already have your infinite collection of operations, of multiplications of 4 elements, but they have a nice geometric structure. It's just a pentagon, a two-dimensional space. Okay. Now, in fact, if you have an operation of 4 elements, you can substitute these operations into each other, just as you compose polynomials, right? So, in fact, there will be a composition of operations and if you have an operation with n inputs and you have an operation with p1 inputs up to an operation with pn inputs, you can substitute these operations for the variables of this operation, and you get an operation with lots of inputs. I will just write it P, where P is the sum P1 up to Pn. Okay? Now, from what I told you, it's not so easy to understand this composition. Okay? Why can you substitute operations? Why can you, if you have a point in this pentagon, why can you suddenly substitute 4 operations and get a new point in some higher geometric space? So to explain that, I will use what Frank Adams called the language of trees. And I will redraw this picture a little bit, but now in terms of trees. So it should be the same picture, but I'm very close to the board, so we have to be careful. W, Z, X, Y. Okay, that's 1 point. And then here we have this tree, X, Y, Z, W. What have you got here? X, Y, Z, W. W, X, Y, Z. Where are we? One more. 1, 2, 3, 4, 5. X, W, Y, Z. Okay, so that's exactly the same figure, right? Now, you can subdivide this space, this two-dimensional space, into squares. I'm going to subdivide it into squares in a special way. I'm going to subdivide this by looking at these trees and by looking at the difference between these trees. And if I contract this edge, or if I contract this edge, then I get the same tree. Okay, and I'm going to put this tree here. Z, W, X, Y. Okay? This type of contraction of edges in trees will occur throughout the lecture, so make sure that you understand what I'm doing. If I contract this edge, Z moves here. If I contract this edge, this pair ZW moves here. It's the same tree, okay? And I can contract this edge here. It's called an inner edge. It runs between two vertices. I have no inner edges left, so I will put this here. So this would be X, Y, Z, W, okay? And I can do the same thing here. And that will be the last example that I will do. So what's the difference between these two trees? I have to contract this edge or this edge. Okay? Then I get this tree, W, and then X, Y, Z. It's again a tree with one inner edge. Okay? And I get a square. So this tree, this is called a corolla, is supposed to index this point. I get this square, and I can fill up the pentagon exactly in a similar way here. I'm not going to name all the trees involved. Okay, so I put another tree with one inner edge here in the middle, and I put a tree with no inner edges. Okay. And now, let's look again at this operation. So, points in here, they can be thought of as lying in one of these squares. Okay? And it's really a path, it's really determined by this tree and contraction of its inner edges. Possibly contraction of its inner edges. Okay? And if you have a tree with n leaves, 4 leaves in this case, and a tree with P1 leaves up to Pn leaves, you can graph these trees on top of the n leaves, and this gives you this operation. Yeah? So you use these trees to parameterize points in this subdivision. You do this also for larger trees with more leaves. You get this operation. So grafting of trees. And this is what makes K, or the collection of the K ends, into an operad. Yeah? So the collection of Kn, bigger than 2 in this case, form an operad. Sorry? Yeah. And so, since some people know, what I've described really is, in modern terms, is a cofiberness resolution of the associative operad. So if you know everything I've said, you can think a bit about this statement. So that's one, and maybe historically the first example of an operad. Okay. Now another historically fundamental example. Maybe it's not so good if I use this board. Can I?
It's okay.
Some people won't see anything. let me not do that. Because what's the first type of operation of multiplication that's only associative up to homotopy, up to deformation, that you teach when you teach the first class in algebraic topology, or if you don't work in algebraic topology, maybe the first thing you heard in a class. That's the loop space of a space, right? So if you take a space X, you can form the loop space omega X. Strictly speaking, you have to fix a base point, so X0, and you look at all the paths in the space from X0 to itself. And you can compose these paths, but you know this is not associative. This is only associative up to deformation, up to homotopy, right? If you have two paths from X0 to X0, you can first run along the one and then along the next at double speed, so to say, if the paths have length 1. And if you do that in a different bracketing, you will have to compare these pictures, these two pictures, okay? So you've probably all seen that. So this can also be governed by an operad, and it's actually a little simpler. Namely, what you can do, you can make a space which is called C1n. So 1 is for the dimension, that's the lines, and the n is the same as this n. Okay? So Cn, and it's the space of configurations of little intervals inside the unit interval with a number. So this could be the first one, this could be the second one, this could be the third one. Okay? And then if you have n loops, you can act by this space. So you have C1 of n times omega x x0 to the n to omega of x x0. So this is like, it has disappeared, but this is the analog of what I wrote when I wrote kn times x to the n to x. But I only did it for n is 3 and 4. Okay. For what do you do? If you have n loops which begin and end at x0, 3 in this case, you put the first loop here at a high speed to make sure that you go from x0 to x0. The second loop here at an even higher speed. The third loop here, and in the intermediate space, you just put the base point. Yeah. So you get a map like this. For any configuration and any 4 loops, you produce a new loop. Okay. So, question?
The endpoints could coincide?
There's only one. Yes. Yes. So 4. That's your question, right? Yeah. But the interiors have to be disjoint. Okay. So this is called the opera. It's again an operad because there is a map like this. Let me use the same indexing. Because what you do, if you have a configuration of n intervals, and you have n other configurations of intervals, p1 intervals respectively pn intervals, you shrink these p1 intervals and you copy them inside here. You shrink the pn intervals and you copy them, and it's 4 inside here. Okay? So shrinking and substitution. And it's a theorem of this goes back to Boardman and Vogt and to Peter May in this language. This is called the operad of little intervals. And the theorem, which in this dimension also goes back to Stashev, is that if you have a space which has all these operations, then it must be a deformation of a loop space. Yeah? Strictly speaking, there's some condition, but this is true for connected spaces, for example. So these algebraic structures characterize loop spaces. And this also works in higher dimensions. So let me draw one, let me go one dimension up. And draw you a picture of C2. C2n is configurations of little squares, but it's better to say maybe little rectangles inside the unit cube, the unit square. So that's a space. So here's a picture of one, two, three, four. This is a point in C2, 4. Okay, so the whole picture is one point. This is a configuration space.
What do you mean by the formation of a loop space? In what sense?
If a space has these algebraic operations, it is homotopy equivalent to loop space. So you can find a map to the loop space and a map the other way, so that both compositions are homotopic to the identity. Okay. Now, here you have the same statement, namely if you can substitute squares inside other squares, so you again have the structure of an operad, this composition structure. So again, well, I'm not going to write it again. It's still here. You can replace this 1 by a 2, so to say, and it works exactly the same way. You have another configuration, so another configuration of P1 many. You shrink it so that it fits exactly here, and you copy it there. Okay. And if a space has operations from this operad satisfying some conditions, respecting composition, for example, it must be equivalent to a double loop space. Any double loop space, omega 2 x 0. So that's omega of x0. You can also view that as the space of maps from a rectangle to x, which send the sides to x0. Okay. The boundary of the square has to go to x0, and inside the square you can do what you like. If you have such a map, you can copy it inside one of these little configurations, and you can keep the base point on the outside, and you get an action. Get a structure on this double loop space. All these operations are going to act here. Yeah. So you have a picture like this. where now this is a 2 and this will also be a 2. Yeah? And again, the same theorem holds. If you have a space which has all these algebraic operations, then it must be homotopy equivalent to a double loop space. Yeah? And this holds for any n. It also holds for n equals to infinity in some sense. Okay. Now there is one. This is called the little cubes operad. So there is something in any dimension, as I said. So let's write down a dimension CD of n, where n is running and d is fixed, is the little d cubes operad, characterizing spaces of the form omega to the d x0, which is the space of maps of d-dimensional cubes into x. Okay. So just to anticipate a little bit about what I will do tomorrow, this is just one choice for this operad, because any homotopy equivalent operad will do exactly the same job. Okay, and there is a whole study of the collection of these operads equivalent to this operad for any d. Yeah, they're called ED operads. So I will write that down tomorrow. It doesn't matter now. And and the fascinating thing is that these operads equivalent to CD can take many different shapes. Some are extremely small and combinatorial. Some are huge and are like compactifications of spaces of these configurations. They're completely different in nature, and they serve different purposes. So we'll look a bit at this tomorrow. And for now, I want to do something more elementary, but still intriguing. Namely, you see, there is a map from, there is a relation between C1 and C2. If you have two configurations of intervals, you can get a configuration of squares. So this gives you a map like this. C1n times C1m to C1 n times m. C2, thank you. C2. Okay, if you have a configuration, let me put it on the side. So if you have a configuration of 3 intervals, for example, and you have a configuration of 2 others, well, I was going to put it on the side. Okay, you get, in the obvious way, configuration of squares. So here's a square, and here's a square. That's correct. So you have to decide how to number these. But let me not go into this now. Okay, and there is a relation, namely, there's a relation for composition. I
didn't catch why are the intervals in the bottom not numbered sort of consecutively?
Well, I don't have to number. I number them. Who asked the question?
I did.
I was with my back too. The numbering is in an arbitrary way. So that space in dimension 1, that space of configuration, since you can contract any interval to a point, this size is sort of irrelevant. It's only the order that matters. So the space C1n is homotopy equivalent to the discrete space of permutations of 1 up to n. Yeah? Okay, so this has to do with the following. If you have an operation of 3 cubes in this dimension, and you put for each an operation of 2, so this is these two, and these two, and you number the edges in some way, then this is going to be the same as this configuration. You can test it in the example. Am I doing the right thing? Yeah. Yes. So you have provided these 3 are the same, yeah, as in this case. Okay. So this is called a shuffle operation. You can shuffle these 3 vertices through this vertex. So if you put the shuffle relation, you get in fact well, the shuffle relation has different ends, but you can reconstruct C2 from C1 using this shuffle relation. So you do this, and you would put a shuffle relation, and I'm not putting an entry here. And this is called the additivity theorem. Additivity theorem. Additivity theorem, which was proved by Dunn, Gerald Dunn, also quite a while ago. And one of the curious things is that I told you before there are many operads which can perform the function of this little cubes operad. So there is something like this true for also for higher in higher dimensions. So let me just replace it here. CP and CP plus Q. Okay. So 1 and 1 is 2. There are many operads playing that can play the role of the little n cubes operad, but it's completely unclear whether they satisfy this additivity or not. So we will talk a bit about this also later. Now, I would like to talk a little bit about the shuffles of such trees in slightly more general terms. So that's a new shuffles of trees.
So there's just 2 operations here.
Yeah.
The black and the...
Yeah. So it will become clear in the next 5 minutes. I take a tree, a black tree and a white tree, and I'm going to shuffle them. Okay. And if you want to think of operads, you can think of the operad freely generated by such a tree. And I'm going to construct the tensor product of two of these free operads. But it's a purely combinatorial thing. So you can forget about operads if you like for the next n minutes. Where n is depending on how fast I go.
Depends on the dimension.
But it depends on the interruptions also. So shuffles of trees. So now I have to look at my notes because I'm going to call out some numbers, and I have to call the right numbers. Here we are.
Are there other operas which satisfy the tensor property?
Yes, but well, that question has a complicated answer. Yeah? You have to derive. One thing you can do is derive the tensor product. The other thing you can do is change it, not derive not derive it, but change it a little bit, replacing this order by a weaker relation, this equivalence relation by an order, for example. But it's a difficult thing. Yeah. Okay. So let's try to shuffle some trees. So this tree, it's a black tree, and a white tree for which I took this tree. So I name the edges 1, 2, 3, 4, and this A, B, C, D, E. Okay? So you should think of the vertices as operations in an operad. So this one takes two entries, entry of type 3 and an entry of type 4, and it produces an output of type 2, and you can have a unary operation which next produces an output of type 1. Okay? And here similarly. Okay? And now I'm going to sort of mix these two operations. Yeah? And in fact, it corresponds to defining this tensor product in some context. But it's a purely graph theoretical thing. So, and I'm going to read it upwards. So I start on the edge named 1 and A. That's the combination of these two edges. Now I choose, for example, to do the black operation. I get into 2A. Okay? The black changes the 1 into a 2, but it leaves the A untouched. Now, let me do a white operation. So I get into 2B and 2C. Okay. Now, here I could do another white. There's only one possibility. I get to 2D. But then I can still do a black. I get into 3D, 4D. And here let's do it the other way around. Let's first do the black. What did I say? 3C, 4C. And then a white. Where's my C? E. 3E.
3D.
What?
Sorry.
E.
Yes, correct. Sorry.
And 4E. It's easier for you because I'm too close to the board. Okay? So that's an example of a shuffle of these two trees. Shuffle. Okay, so I hope I made it clear that I made some arbitrary choices, right? After the black, I could have done another black, or I could have started with a white, and so on. How many ways can you do this? In this particular example, it's 14 trees. So shuffling gives 14 different trees. Yeah? So if you ask yourself how many trees you can produce using shuffling, there is one example that you all know, namely there's also the trees which have unary operations only. Yeah? They're just linear orders. So shuffling linear trees So you would have a white linear tree. How did I number them? From 1 up to n, and from 0 up to n maybe. And so it has n vertices, and a black one with n vertices. How many ways can you shuffle those? Well, you pick either a black vertex or a white vertex, and until you run out of the vertices, and it's just n plus m over n. N plus m choose n, right? So everybody knows that. And it's a nice small number. So this is a bit large, but because the trees are quite small. 14. So unexpectedly large, perhaps. So now I really need to look at my notes. So here's another small example. How many shuffles of these two trees, S and T, the white tree and the black tree? I've talked about this before. Did I make a mistake?
An edge.
An edge, yes, thank you. Who thinks more than 10? Well, of course, they're larger than 14. Who thinks less than 100? Who thinks more than 100? Who thinks more than 1,000? Who has heard me talk about this before? Who thinks more than 10,000? Okay. So you're in the right range. 3,089 shuffles. And it's a prime number. So it's a very simple operation that I'm using all the time, because this generates the tensor product of operads. You write an operad, you resolve an operad by 3 operads. You take the tensor product by shuffling trees, and then you push back, if you like. So it's a very fundamental operation, which we understand reasonably well topologically in some cases, but which we do not understand at all combinatorially. Yeah? So I really don't understand where this number comes from. So I wanted to leave you with this mystery, so as also to have something to think about, even if you're already an expert in the theory of operads. I can prove a few things about it. Not very many, though. So here is one statement. If you shuffling a tree S with a linear tree N, so this is N, can be done in, let's say, PS of N many ways. And then PS of N is a polynomial. Okay, so it takes an integer n as input and a natural number, and it spits out another natural number, but it has rational coefficients. With rational coefficients, and degree the number of vertices in S. Okay? And the leading coefficient is what I like to write as 1 over s factorial. Now what's 1 over s factorial? So s factorial is the product over all vertices in S of the number of vertices in the part of the tree which is above that vertex V. So if you have a tree like this is a tree S, you pick a vertex V to have an output, and there will be a part above it. So I call this tree the upper arrow V. So V is, the vertex V is part of this tree in the count. Okay, if you do that for linear trees, you get the usual factorial. So that motivates the notation. Okay, so that's one of the very few things we can prove about it.
What's the point? I'm using operads.
Sorry?
The proof of this one is using operads.
No, the proof.
Just combinatorial.
Yeah, it uses some number theoretic formulas, Faulhaber's formula, for example. So this is purely combinatorial, but the motivation comes from operads. So if you cannot count something, one thing to do is to try and put some structure on it, right? What is the structure? What is the structure of all the shuffles between two trees? Well, it's a finite thing. It has a natural partial order, where you say that the white one dominates the black one, for example, and you can do it upside down. And it's a lattice. For any two shuffles, there is sort of a smallest shuffle under it, over it, and a largest one under it. Yeah? And there is a biggest one in the order where you put copies of the black tree on top of the leaves of the white tree, and there's the smallest one where you do the other way around. So there is some structure there, but it's quite mysterious. Yeah? So
And for
if
binary trees?
sorry.
For binary trees? Do you know?
Yeah, a good question. We thought about this. We don't know. So if you want to read more, I wrote a paper about this with one of my collaborators, Erik Hofbeck. It's my only paper in the combinatorics journal. And where we describe the structure and maybe we count a few more examples. It's a mystery. It seems very simple. I also tried sometimes to motivate this to computer scientists by doing some sort of parallel non-deterministic programming. You see, this is a non-deterministic program which has a step from 1 to 2, and it has a possible step from 2 to 3 or from 2 to 4. Yeah? So it's a sort of non-deterministic. Now you let these two non-deterministic programs run in parallel. So the computer can only do one step at a time. So it has to decide whether it invokes the black program or the white program. Yeah? So there's one way to think about it intuitively, but I still cannot count. So it's not entirely a joke because, as I said, this construction occurs all the time when you work with operads and related structures. Good. So that's basically the end of the introductory hour. So let me say a few things about what I will do tomorrow and the day after.
Shuffling of trees occur all the time to operads?
Because the tensor product of operads is an important operation because it describes, for example, I haven't talked about algebras over an operad, but I did talk about these operations, like we had things on the board like k4 times x to the 4 to x. Okay, so if a space X has these operations, but then for any n and satisfying certain conditions, with respecting the composition, for example, you call X an algebra for this operad, the Stashev operad K in this case. So a P tensor Q algebra is the same as a P algebra in Q algebras, or a Q algebra in P algebras. It's also symmetric. Yeah? So you can build up more complicated structures by writing them as tensor products of simpler ones. So
Connected to the gray tensor product somehow?
I don't think so. No. So if you do this, maybe to answer your question in a more in a slightly different way, if all the operations are unary, yeah, then the operad would be like a monoid, or if it's a colored operad, it would be like a category, and the tensor product would just be the ordinary product. Yeah? Not the gray tensor product, not the gray product, but the ordinary product.
Can I ask, earlier you had another example on the board where you shuffled two trees in two different ways, and you said they were equal.
Yes, I can. Yes, I wasn't very precise about this, more or less on purpose. But so if you want to define P tensor Q in a more precise way, so P and Q are operads, and they are, for the specialist, they are uncolored. So P is a collection, let's say, of spaces P of n, and Q is another collection of spaces Q of m, n and m running. Then you try to make, so we had these substitution operations, right? If you have an element of P of n, you can put n other operations inside it. So you start now doing this for the operations of P and Q together. So if you have an operation in little p in P of n, so it has n entries, you can get a new operation here by substituting here a Q, and here maybe another Q primed, and here maybe a Q double primed. But you cannot compose. Okay? If you put another Q above it, you could compose. But if you put P's here, you cannot do anything.
It's an equivalence relation on all these shuffles.
Right. So these trees, these labeled trees, where any vertex here has a P on one side and a Q on another side, or vice versa, generate this P tensor Q. But now there's one relation, namely, and that's related to my statement that you have a P algebra and Q algebras, or a Q algebra and P algebras. If these Qs were all the same, then you can switch. So this operation, and it's sort of local. If these were all the same, Q, 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 and there could be lots of stuff above here, then this will be the same as you put a Q. So let me give it a different color. And now Q may have not 3 inputs, but 27 inputs. So you put 27 edges here. You start, and then you repeat your P, 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 P. And you will see that the number of edges here, immediately above, is the same as the numbering here, but the order has changed. Okay? So you can still complete the tree. So that's the local equivalence relation. Yeah? It's local equivalence relation. Operating on such things. Okay? And so that's exactly a shuffle. Yeah? Yes?
May I ask you one basic question? Could you compare for us operads with algebraic fields, for example, for that matter, the little group operads or single group machine? Why are you interested in operads and incorrect other?
Well, one of the forces of algebraic theories is really in a Cartesian context, and operads is in arbitrary symmetric monoidal context. Yeah? So it's a bit more general from that point of view.
Unpointed spaces, they have the same strength of expression.
Yeah. Well, okay. let me not go in. There's some more subtle differences, but the main difference is that. So, for example, if you take an operad in spaces and you take its homology, you get an operad in graded vector spaces, for example, which is not a Cartesian category for the symmetric monoidal structure. You could look at algebras in that category. So, the theory of operads is easily moved from one context to the other, and that's not so much true. Not true in the same way for algebraic theories. So I think that's one of the main forces of theory of operads. For example, this operad C2, if you take its homology, you get the operad which governs Gusten-Haber algebras. So it's related to Hochschild homology. And that maybe is also a way to make a little jump to tomorrow's talk. So the Hochschild cohomology has a Gusten-Haber algebra, so it's an operad. It's an algebra for the operad obtained by taking the homology of what I call C2. Yeah. And you can ask, and there was a question posed by Deligne, can you lift this to the chain level? Yeah. Is there an operad which acts on the Hochschild co-chains? And you cannot take the chains apparently of these spaces occurring in C2. So people started to look for models of C2 for which this thing could be lifted. Yeah? And that was one of the inspirations to look for small combinatorial models of, in this case, little 2 cubes operad or higher variants of it. So that's one of the things I will talk about tomorrow. And the main player in this area is a very simple combinatorial operad of graphs. So you can imagine that if you have, if P of n, this P of n is somehow some sort of space or structure or category or chain complex on graphs with n vertices, you can substitute. Because you can replace a vertex in a graph by another graph. Yeah? You get a bigger graph. And this gives, we will see tomorrow in detail, this will give you an operad structure. And a special kind of graphs will be key in comparing all these operads that are that act as like the little n cubes operad. They're called En operads. So that's tomorrow. You had another question?
Yes, could be. This polynomial phenomenon looks very much like a Hilbert phenomenon. So the question is maybe there is an algebraic source
Hey?
for these meanings.
Sorry? What kind of polynomial?
Hilbert polynomial.
Hilbert polynomial.
So instead of stiction, you have the degree and you have a factorial in the bottom. So I wonder if there is any source, an algebraic source of this.
Yeah, I cannot answer your question. We asked many people, and we put the for various sequences of trees. We put this in this encyclopedia of number sequences or something like this, and we didn't find anything. So I would be extremely happy if one of you could say something more structural about it. But I'm not a number theorist, so I hope to see you tomorrow.
So we'll take questions in the virtual auditorium. Okay, so let's see. I guess I should read the question. There's a question from the chat.
Yes.
Maybe you could repeat it if you don't mind. They ask, in the example, in general, how many white dots and black dots must have any shuffle? Again, I'm not sure if the question is understandable.
Yes, I think I understand where the question comes from, at least. So the question is, how many white and black dots does a shuffle need to have? And you see, what you see maybe in this example, if P has 3 inputs, you have the same operation Q can occur with multiplicity 3 somehow. Okay, so there are these multiplicities, vertices get repeated. So here the same white vertex from C to E occurs twice here because it occurs above a binary black vertex. So the trees get very wide. Even if you start with narrow trees, they can get very wide. And there's all kinds of multiplicity phenomena going on when you go up the tree, which are very difficult to control. Yeah? So I cannot answer the question in a precise way, but I understand that this is a bit mysterious if you look at it for the first time.
May I ask a similar question? The different shuffles, probably they don't have the same number of...
Correct.
Would you mind repeating it?
The question in the audience is, if you take 2 trees and you look at 2 different shuffles of the tree, they can have different number of vertices. That's true. Yeah.
So can you split this number into kind of depending on the number of black and white vertices, or some kind of get some more meaningful? So instead of counting all shuffles, put them with these coefficients depending on the number of white and black dots, or somehow, I don't know.
I do not understand the question. I can perhaps mistranslate it into some things that you have in mind, like binary trees, ternary trees. If you're fixing the shape of a tree, so here I fix the shape of one tree to be linear. That's one of the few cases I can control to some extent.
All right. So in these shuffles, if I just tell you precisely that I want only to count shuffles with a certain fixed number of white and black dots.
Okay. Yeah.
How many are there? So can you split in general?
I see what you mean.
It by the number of white and black.
I don't know a formula for
dots,
this.
and
I don't. Yeah.
to get maybe that would be
Yeah.
kind of some kind of more interesting object.
Yeah.
On which you
Yeah.
can
That's
really
that's
see some
that's
structure.
possible. I haven't looked at it from that point of view. Maybe I should have said there is an easy inductive formula for shuffles. Yeah. Any tree. Any white tree is a white vertex with a family of white trees on top of it. Okay, and the same for a black tree. So if you shuffle a white tree and a black tree, you have to decide, let's say I start with a white vertex on the bottom. What remains is shuffling this tree with the original black tree, and this tree with the original black tree, and this tree with the original black tree. So that's a product of the number of shuffles of these three. So there is an inductive formula which you can write down, but there is no closed formula. And of course we use the inductive formula for this.
So we're going to resume tomorrow at 2, and let's thank the speaker again.
The number of citations for your only combinatorial paper, does it fit into your sequences?
Well, I
Is
don't.
it more than all of your other
No, I think
citations together? You know,
yeah.